Okay, today we're going to learn how we describe energy. So this is going with Learning Target 19, explain how frequency and wavelength relate to the amount of energy. Okay, so a wave is any rhythmic disturbance that carries energy but not matter. So energy travels as waves. And there's different properties that a wave has that's going to determine how much energy a wave will carry. So amplitude, if you increase the amplitude, it increases the energy and loudness. That's why you guys can sometimes see cars that have amplifiers and the car is like bouncing up and down because it's the music so loud. Amplitude is the distance between half of a wave to the top or half of a wave to the bottom. So this would be amplitude, except it would be straight up and down. So it's that half of the wave to the crest, half of the wave to the trough. That's your amplitude. So the higher or taller your wave is, that's going to give you a larger amplitude. Wavelength is the distance from crest to crest, trough to trough. So here is an example of wavelength. This symbol right here looks like an upside down Y. That's the symbol for wavelength. Okay, wavelength has an indirect relationship with frequency and energy. If you increase the wavelength, so the larger distance between the waves, that's going to decrease your frequency and decrease the amount of energy that wave can carry. Okay, frequency is the number of wavelengths that pass a given point in a certain amount of time. Okay, so if you take a look at these three pictures, okay, they all have different wavelengths. Notice the bottom picture has the largest wavelength, next smallest, and then the smallest is on the top. Okay, there's a indirect relationship with frequency and wavelength. So what you do is you count the number of waves that pass a given point. So here's a wave, wave, wave. So in this case, there were 4 waves that passed a given point. Then if you come up here, 1, 2, 3, 4, 5, 6, 7, 8. 8 waves pass. Up here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 waves pass a given point. So the wave that has more waves past a given point have a higher frequency. So if you notice, this had 16 waves that pass a given point. Look at its wavelength. It's the smallest. So that's why frequency has an indirect relationship with wavelength. So if wavelength increases, then your frequency will decrease. If wavelength decreases, your frequency will increase. Now, frequency has a direct relationship with energy. The more waves that pass a given point in a certain amount of time, the more energy that wave can carry. So if you increase frequency, you're going to increase the amount of energy that a wave can carry. Wave speed is basically counting how fast the wave is moving. So you're going to take your frequency and you're going to multiply that by wavelength. Okay, pitch also has to deal with the amount of energy in a sound wave. So if you have a high frequency sound wave, you're going to have a lot of energy, so your pitch is going to be greater. So to give you an idea on pitch, if we take a look at these two frequencies, these are both sound waves. If we increase the frequency to the highest point on this app, okay, notice how tiny the wavelengths are. So they have a lot of frequency. They have a lot of waves passing a given point. So they should have a lot of energy. So let's listen to the pitch. Okay, now let's decrease the frequency. So now notice the wavelength increased, so we decreased our frequency, so we're going to have less energy. Now let's see what the pitch does. The pitch gets lower because it has less energy in a sound wave. Okay, so those are the properties of waves, and then we're going to talk about different types of waves. We just saw a sound wave and how it relates to energy and pitch. There's also seismic waves. Those are the waves that are produced from earthquakes that will carry the energy from earthquakes. We have electromagnetic waves that come from our sun or stars, light waves, visible light waves, which are actually part of the electromagnetic wavelengths, and then water waves, etc. We have a lot of different types of waves. The one we're going to talk about the most right now are electromagnetic waves because it directly relates to our next unit, which is in space. Waves, electromagnetic wave is a wave that can travel through space. So it's produced by charged particles that move, those electrons that move. So that's what's coming from our stars when nuclear fusion is occurring on the surface of stars and creating energy. That energy travels as an electromagnetic wave. Electromagnetic waves travel at 300,000 kilometers per second, which is the speed of light. Okay, in an electromagnetic wave, it can be broken down into parts. That energy that is released by the sun contains a lot of different types of energy. So it's a wide range of waves that have different frequencies and wavelengths. So our electromagnetic spectrum carries a lot of different types of waves that carry different types of energy. So if we take a look at this electromagnetic spectrum, we've got radio waves, did not mean to move that. Radio waves, microwaves, infrared waves, visible light waves, that's what we can actually see coming from our sun, ultraviolet rays, X-rays, and gamma rays. Now if you notice below, on the electromagnetic radiation that comes from the sun, we get a variety of wavelengths and frequencies. Okay, radio waves have the largest wavelengths, so they have the smallest frequency, the least amount of energy. Gamma rays, if you notice, have very small wavelengths, so they have a very high frequency. They have the most energy. Luckily, our atmosphere protects us from X-rays and gamma rays because they have the most energy and they can actually harm us. That energy from gamma rays can actually travel through our skin into our cells and damage the DNA in the nucleus of our cells. So we do not want to get exposed to these types of radiation. So that's why our atmosphere is so important. It blocks the sun's it blocks these waves from reaching the atmosphere or reaching us. Our atmosphere blocks some of the ultraviolet radiation from the sun, but not all. That's why it's always so important to wear sunscreen when you go outside so you don't get exposed to the ultraviolet radiation. And then the rest of this, our atmosphere does not block. And that's why we're able to see light coming in. That's our visible light spectrum. And if you take a look, we can break our visible light spectrum down into colors. That's our Roy G. Biv. Red has the largest wavelength, least amount of energy and smallest frequency. Violet has the highest. We talked about this in 7th grade when we were talking about adaptations of creatures of the deep, because blue light is the light that travels the farthest in the ocean. Some of your organisms that want to camouflage will be red because you can't see red light down deep. So that's our visible light spectrum. Okay. Now, one thing we're going to talk about and help you guys understand the relationship between wavelength and frequency is we're going to look at an emission spectrum. So this is the light that is released from an element that has been heated. And when elements are heated, they're made up of 7 different colors that are mixed together. When they're separated, they create a fingerprint for each element that helps us identify that element. We use this in space. So if we want to find out what types of elements are in a planet's atmosphere, we can use this emission spectrum to discover that. So if you take a look below, if we heated up hydrogen, we're actually going to do this in a lab, if we heated up hydrogen gas and then looked through it in a diffraction lens that will separate the light into its colors, you will see that hydrogen is made up of red. Oh, I did not mean to move that. It keeps doing that. Red. Okay, I think I got it. Red light, some blue lights, and some violet lights. And it's like a fingerprint. No other element will have this band of light fingerprints. Like that's what we call it, the emission spectrum. Each element is different. Sodium only shows 2 wavelengths of yellow light. Helium, you can see helium. Neon's pretty cool. It's all reds, orange, and yellows. Mercury down below. So you're wondering, well, how does it do this? How do these elements do this? Well, electrons, and we haven't talked about orbits a whole lot. We talked about it a little bit in 6th grade. But remember, electrons surround the nucleus of an atom. Inside the nucleus are your protons and neutrons. Electrons are located in orbits around the nucleus of an atom. And when electrons move into different orbits, they'll do this when they're heated. They become energized and they release a photon of light when they go back to their original orbit. The light is what creates an emission spectrum. So for example, if this is an electron and this is its normal orbit that it rotates around the nucleus of an atom, we heat that atom up. It will become energized, have more kinetic energy, so that electron will jump into the next orbit. Then what happens is that kinetic energy is transferred into the atmosphere and the electron will fall back to its original orbit level. When it does that, okay, when it falls back down, it releases some of that kinetic energy, gets transferred into light energy. That light energy is this emission spectrum that we see from the elements. These are the electrons that are bouncing around from orbit levels. When they go back to their orbit level, they're going to transfer that kinetic energy into light energy, and that's your emission spectrum. Okay, to show you what that looks like, okay, so that's an electron moving around an energy shell. It's going to release. That's what that orange light is getting released. It's going to release photons of light when it jumps back and forth from energy levels. Okay. And you guys are actually going to do a lab with this activity, and you're going to show the relationship between wavelengths and frequency. So if we look at this hydrogen atom, if you look at the electrons, when they get energized and they go from orbit level to orbit level, they fall back. If you notice, this is the color of light that kinetic energy gets converted to. So electrons that are closer to the nucleus, okay, release certain colors. The farther away they get from the nucleus, they release the different colors on our visible light spectrum. So this is kind of what this graph is showing you. Okay, if you jump one orbit level, it's going to release a yellow light. If you jump to 3, green. If you jump to 4 energy levels, you're going to be blue. 5 energy levels, you're going to show 5. You're going to have violet. If you jump from energy level 2 to energy level 5, there's blue light. So these are the different photons of light colors that are going to get emitted as the electron moves to the different orbital levels. And that's what's represented by the 1, 2, 3, 4, and 5. Those are the different orbital levels. So as an electron jumps from different orbital levels, if it jumps from 1 to 2 orbital level, it'll release a yellow. And that's what this is showing you. Okay, so hopefully that gives you a better understanding of how energy is going to travel as waves, some properties of waves. And now you will actually be looking at a lab and looking at those emission spectrums of different elements, and then you'll be working with the relationship between wavelength and frequency.